we're going to think a little more deeply about how exactly or what exactly matrices are representing. Other than just being the coefficients of linear systems, we'll see that matrices actually have some subspaces of Euclidean spaces and some important numbers associated with them. And to get this all started, first we need to just note that after any sequence of row operations, the resulting rows in the matrix at the end are linear combinations of the initial rows. Now, if you just think about what the individual row operations do, this might be pretty clear, but just to make it precise, we'll actually write out a proof. And we'll do this in 2 steps. So the first thing that we'll show is that each single row operation, or after a single row operation, the resulting rows are linear combinations of the starting rows, the rows that you started with. Okay, and this will be easier to show because we only have to deal with the row operations one at a time. And the second thing that we'll show is a linear combination of linear combinations is itself a linear combination. Now, once we've proved these 2 facts, this will prove what we want, because if we start with some matrix and do a row operation to get another matrix, and then do another row operation to get a third matrix, and so on, at each step, after each step, the rows of the new matrix will be a linear combination of the rows before. So this is true at every step, linear combination of rows from the step before. But if linear combinations of linear combinations are themselves linear combinations, then that means rows from this later step are linear combinations of these linear combinations, and so rows from later steps will be linear combinations of the things we started with, or the rows that we started with. So if we can show these 2 individual facts, then together they combine to prove what we want. So let's prove the individual facts. So let's show that after a single row operation, the resulting rows are linear combinations of the starting rows. So we only have 3 cases to check, because row operations only come in 3 flavors, right? Row interchanges, scaling, and adding a multiple of a row to another row. So to prove our first thing, let's check row interchanges, row switches. Okay, so if we have a matrix, and for the rows of this matrix, I'm going to write the rows as A1 through AM. We don't know how many rows there are, but if we switch row I and row J, where I and J can be any 2 rows, what we get is, AI is in here somewhere, and AJ is in here somewhere. What we get is A1, and then all of the rows in order up to where in position I, we used to have AI, but now we have AJ because we switched them. And then in position J, we used to have AJ, but now we have AI. And then down to the last row, whatever that is. Okay, so is each row here a linear combination of the rows that we started with? Well, yes, clearly, right? The first resulting row is the same as that row, and so on, down to the jth row. The jth row isn't equal to the the ith row, which is AJ, that we end up with, isn't equal to the ith row that we started with, but it is a linear combination of all the rows, because it's actually just the jth row. And, similarly for AI and all the others. So that checks it for row switches. For scaling a row, if we take all our rows, if we multiply the ith row by a constant, the resulting rows are A1, and then in the ith position, So here's the ith row here. We get C times the AI that we started with, and then down to A sub m. Okay, is each row here a linear combination of the rows that we started with? Well, yeah, they're all the same except for the ith one, but the ith one is just a constant times the row in that position that we started with. So, right, the ith row is a linear combination of all of them. In fact, it's a linear combination of just the ith one. Okay, last thing to check is adding a row, adding a multiple of a row to another row. So let's say so here are all our rows. And let's say we add to row j, we add a multiple of row I. Okay, so what are the resulting rows? Well, the first row is still A1. That hasn't changed, so that's a linear combination of the rows we started with. The ith row is actually still equal to the ith row, so that's a linear combination of the rows we started with. The only row that has changed, right, all of these are the same, the only row that has changed is the jth row. And in the jth row, we have A sub j plus C times A sub I. And this row is a linear combination of the rows that we started with, right? This here is a linear combination of AI and AJ. All right, so each individual row operation produces rows that are linear combinations of previous rows. So that proves our first fact, right, number 1. So this one's done. Now we just need to check our second fact, that a linear combination of linear combinations is a linear combination. So to do that, right, let's suppose that we have some vectors. Maybe I should call them A1 through AM just to match the notation from the previous argument. So what would a linear combination of this look like? So a linear combination is something like, right, B1A1 plus dot 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 down to BMAM, right? So, but we might have several different linear combinations of the A's. So I guess I should write linear combinations are. Okay, now we're going to have several of these. So this is our first one, and we're going to have many of these, so maybe n of these down to the nth. And to denote which linear combination we're talking about, I'm actually going to add a subscript. So actually I need to change this a little bit. I'm still going to use b's for the coefficients, but for which linear combination we're talking about, that'll be my first subscript. And then which vector this is the coefficient for will be my second subscript. So this is B11 down to B1M. And then we have all these different linear combinations down to BN BN1 A1 plus dot 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 down to BNM. So because of a quirk of how I did the indexing, the n is the first index and m is the second index, but that's okay. So here are a bunch of different linear combinations. So now let's do a linear combination of these linear combinations. So we might have C1 times the first one, B11A1 plus and so on down to B1M AM, and then plus, right, every linear combination from this list here will have a coefficient that's C sub something down to C sub n, B n1 A1 plus dot 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 plus B n m times AM. Okay, so our question is this a linear combination of the A's? Right, we know it's a linear combination of these linear combinations, but is it a linear combination of the a's? Well, just gather up the coefficients on each a, right? So we have a bunch of a1 terms. What do they all look like? Well, there's c1b11, and then in the next term here, there's another term that has a1 in it. That's going to be c2b21, and so on, down to this last one, which is going to be cnbn1, right? And then we get a similar thing for every other a, right? There's a down to am. The first term here is going to be coming from this one, so that's c1 times b1m plus, and so on, right? There's one of these in every term, down to the last one, which is going to be cn bnm times am. There we go. So is this a linear combination of the AIs? Well, clearly yes, right? Just because it's some coefficient times a sub 1 plus some coefficient times a sub 2, and so on, all the way down to some coefficient times a sub m. So that shows that a linear combination of linear combinations is a linear combination. So that proves our second thing here. And so we've finished proving this fact. After any sequence of row operations, the resulting rows are linear combinations of the initial rows. So this is now proved. But what this is telling us is that if you think about all the possible row operations you could do, what you can get is the entire span of the rows that you started with, which that kind of inspires the definition of the row space of a matrix. So if you have a matrix, the span of the rows is called the row space, and I'll write it like this: row A. This isn't totally standard notation. Some sources actually write out the word row space, but I can't be bothered to write out row space every time, so I'll just write row A. Notice that if A is a matrix with m rows and n columns, each row has n entries, and so the row space of A is actually a subspace of Rn. All right, so, right, and again, the reason why you would think about the span of the rows is because all of the rows that you can get to by doing row operations, they're all in this row space. All right. Well, now that we have a subspace, we could ask ourselves, what is the dimension of that subspace? And we'll name that the rank. So the rank of a matrix is the dimension of the row space. You might think we should call this the row rank, and indeed some people do call this the row rank initially, but I'm going to call this the rank for reasons that you will see later. All right, so row space is just the span of the rows of a matrix, and the rank of a matrix is the dimension of the row space. All right, well, two quick facts about row space for a matrix. First is that row operations don't change the row space of a matrix. So again, we can prove this stepwise. So what we'll do is we'll just show that no single row operation changes the row space of a matrix. If no single row operation changes the row space, then a whole chain of them won't change the row space either. So let's suppose that we have done some row operation here to get to a new matrix B. Right? We know from before that the rows of B are linear combinations of the rows of A. Right, we proved that earlier. So this means that the row space of B is contained in the row space of A. Right? The row space of B is every linear combination of rows of B, but every row of B is a linear combination of rows of A. So linear combinations of rows of B are linear combinations of rows of A. But we know that linear combinations of linear combinations are linear combinations. So everything in the row space of A is a linear combination of rows of B, which means that it's in the row space of A. So row space of B is contained in row space of A. But another thing we know about row operations is that every row operation is reversible, right? With another row operation. Right? If you switch two rows, you can switch them back, which is a row operation. If you multiplied a row by a non-zero constant, you can undo that by dividing that row by the non-zero constant. And if you've added a multiple of a row to another, you can undo that by subtracting the multiple of the row for another. So every row operation is reversible with some other row operation. So that means this row operation that turned A into B, there's another row operation that turns B into A. But then this exact same argument on our reversing row operation shows that the row space of A is contained in the row space of B. Well, look, if the row space of B is a subset of the row space of A, and the row space of A is a subspace of the row space of B, that means that they're actually equal. So the row space of A is equal to the row space of B. Okay. And so we've shown that no single row operation changes the row space of a matrix, and that means that no chain of row operations will change the row space either. So, another interpretation of what row operations do is they just sort of give you different spanning sets for the same row space. All right, well, I said the magic word spanning set. What we would prefer from a spanning set is to have a linearly independent spanning set, because that would be a basis. Well, we know we can do row operations to get to reduced row echelon form. And the reduced row echelon form is nice because the non-zero rows of a reduced row echelon form matrix are linearly independent. And this means that, once we have proved that this is true, we know that the rows for the reduced row echelon form span the same row space as we started with. But if we also know that the non-zero ones are linearly independent, that will mean that the non-zero rows of the reduced row echelon form of A span, or are a basis for the row space of A. Okay. And knowing a basis for a row space, that tells us a lot of things. In particular, it will tell us the dimension of the row space. In other words, the rank of the matrix, So we defined rank earlier, but we didn't really have a way of figuring out what the rank of a matrix is. This will give us a way to figure out the rank of a matrix, Do a row reduction, and then you'll be staring at a basis for the row space, so you can just count the non-zero rows, and that'll tell you the rank of the matrix. Okay, but of course we have to prove this first. So prove that the non-zero rows of a matrix in reduced row echelon form are linearly independent. What we'll do is, this is really more of a sketch of a proof. I'll leave the details to you. Sort of writing all the indices down is surprisingly annoying, but the idea is very clear. So reduced row echelon form has this stair-step pattern to where the pivots are, And everything below the pivots is all zeros, like this, Okay, so now let's ask, can a higher row be in the span of the lower rows, of non-zero rows beneath it. Okay, so right, taking this row as an example, is it possible that this row is a linear combination of non-zero rows beneath it? Well, the answer is clearly no, because linear combinations of lower rows always have a 0 in the pivot position for this row. Right, so this pivot position here, rows below it always have zeros in that position, and so any linear combination of lower rows will never give you something non-zero in this pivot position, and so the linear combination of lower rows can't produce this row because they can't get that 1 there. So so higher rows can't be in the span of lower rows. All right. Now this is actually enough to show that we have this is enough to show that the non-zero rows form a linearly independent set because of this, right? So first, consider the collection of just the lowest non-zero row. So V1 is the lowest non-zero row. This collection is linearly independent. Right? If you have a single vector that isn't 0, it is definitely linearly independent, right? Okay. Now, this fact that we showed before, if we let V2 be the next row up, so I'm kind of numbering my rows backwards so that V1 is the lowest non-zero row, and then that V2 is the next one up, and so on. So right in my diagram, this would be V1, this would be V2, this would be V3. So if we take the next row up, we know that this is not in the span of V1, right? That's what we just proved. Higher rows can't be linear combinations of lower rows in reduced row echelon form. So we know that if we start with a linearly independent set and add a vector that's not in the span of that linearly independent set, it's still linearly independent. So this shows us that V1 comma V2 is linearly independent. Well, now we can just repeat the process, right? V3 is the next non-zero row up. We know that V3 can't be in the span of V1 and V2, again, because we proved that up here. Higher rows can't be linear combinations of lower rows. So V1, V2, V3 is linearly independent. All right, now we can just repeat this whole process until we run out of rows. Right, as we move up, right, adding more and more vectors to our linearly independent collection, eventually we run out of rows because the matrix only has a finite size. And when we've done that, we have the linear collection, our linearly independent collection is all non-zero rows. Right, and we know that this is linearly independent. All right, so that proves that in any reduced row echelon form matrix, the collection of non-zero rows is linearly independent, and that means that the collection of non-zero rows is a basis for the row space of the matrix.